Okay, I think that's started. Good. We are looking at exercise 3C from the textbook. This is the section on finding stationary points. Determine position and nature of stationary points on the interval x lies between 0 and 2 pi radians. Show a graph of the function, and here's the function I'm going to look at, f. Thought this one was a bit harder. And I've used an angle identity in it because that makes the question a bit easier. So stationary points happen when the derivative is equal to 0, right? i.e. the gradient equals 0, or the rate of change of that function equals 0. So we need a derivative. Okay, so we could write f prime x equals derivative of sine is cos. Now that's an outside operation, so I'm making cos 2x, then I'm looking at the inside. Derivative of 2x is 2, plus derivative of cos is minus sine, right? So I'd have plus 2 times minus sine. Let's just go straight to writing minus 2 sine x. So there's your derivative. You're getting stationary points when the derivative equals 0. Let's put the 2 out there. When 2 cos 2x minus 2 sine x equals 0, we can go through and divide by 2. Right, so we could say cos 2x minus sine x equals 0. We could say, let's add sine x to both sides. When does cos 2x equal sine of x? Because when this happens, our derivative equals 0. Now, I'm going to draw a unit circle because there is, in quadrant 1, I think there's a point that stands out pretty clearly. However, there's 3, right? So in one revolution of a circle, this happens 3 times. Now, here's the first one. Right, there's your pi on 3. Sorry, pi on 6. And then if I go to pi on 3, right, now the cos is a half, the sine is root 3 on 2. This is a unit circle, right? 1, 0, 0, 1. So what I'm trying to point out is that when we've got an angle of pi on 6 in there, right, sine pi of 6 is a half. I'm looking at that. If I took the pi on 6 and put it in here, 2 times pi on 6 is pi on 3. It's this angle. And now the cos, right? So cos of pi on 3, because it's been times by 2, right? See where I'm going? So x could equal pi on 6. That fits this criteria. It provides us with a stationary point. Now, I haven't done anything too fancy there. I'm just inspecting the unit circle. There is another one here. The problem with this is I think it's easy to miss them. Right, so we are going to do this a slightly different way in a minute. But if I took 5 pi on 6, I think that's the next one from memory. then the sine would be a half. Now if I double 5 pi on 6, I get 10 pi on 6. That's the same as 5 pi on 3, which takes me here, where the cos is a half. Sine is minus root 3 on 2. So that works. So you could sort of scour through your unit circle and look for them. There is one more. I think it would be easy to miss. It's this angle here. I go all the way around to 3 pi on 2. Sine of 3 pi on 2 is minus 1. All right, that's easy. When you come to put the 3 pi and 2 in with the cos function here, you're going to double it. So 3 pi on 2 doubled is 6 pi on 2, that's 3 pi. So what's cos of 3 pi? Right, that's pi, 2 pi, 3 pi. I'd be here at minus 1. So again, that number, this is probably the one that would be the easiest to miss, I think. So if I made my angle go to there, 3 pi on 2, right? I put it in here, sine is minus 1, I put it in there, gets doubled, becomes 3 pi, cos is minus 1. So that's the other solution, all found by inspection. If I found them all, I could then go to the sine diagram, right? And that would be fine. You'd probably want some working where you're showing your unit circle. Right, so here's how to do it without a unit circle. Well, I think you still need the unit circle actually, but you can do a little manipulation. Oh, this is what I'm trying to do here. I'm trying to go to your trig note sheet. There it is. Right. Whenever I see this cos 2x, this is complicating things. Maybe I can undo that. We've talked about this in class. We know we can undo that using the double angle formula. There's actually 3 for cos 2x, or 2 theta, same thing. We could change it to this one, cos squared minus sine squared. But then I'll have a cos, a sine, and another sine. Be nice if I could change this cos to something that's a sine. I think that'll simplify things. I could have, so this is the one here, 1 minus 2 sine squared theta. You might still be a bit worried because you're thinking, well, that's a sine squared, but we'll show you how you can work with that in a minute. So I've just got to remember this, 1 minus 2 sine squared. What am I doing? I didn't want to do that. I want to do this. 1 minus 2 sine squared. Right. So I've got my pen back. Yeah. Don't need that. So from this point here, we'll pretend that we didn't find these. We could say, therefore, 1 minus 2 sine squared x equals sine x. What I would write is double angle formula for cos, or maybe I could just say cos of 2x equaled 1 minus 2 sine squared x. We showed how to get that in class, where I drew it. I did it from drawing two right-angled triangles on top of each other. Anyway, next I'm going to make this a quadratic. So what I'm going to do is reorder this. I'm going to say 2 sine squared x. It's like I'm adding that to both sides, plus sine x minus 1 equals 0. Right, so I've done a bit of arranging to try and put this into the form of a quadratic. Okay. Now I think it's easier to get rid of the signs at this point. So firstly, can you see that you've got something squared plus something plus a constant or minus a constant? That's taking on the form of a quadratic. If you saw it like this, you could probably think about solving for x with that. I hope so anyway, because that would be like a year 11 sort of quadratic that you could solve and find out what x is. You could use quadratic formula if you got really stuck. What I've done to make it look more like a regular quadratic, I've said, curly brackets, let sine of x equal just an x. Now it looks a bit easier to work with, and then I could think, well, let's factorize it. If we want to solve for x, it always helps if we can factorize, because then we can use null factor law. So I think, well, how can I make the 2x squared? Oh, I know, 2 times 1. So 2x times x is the only way you're going to get the 2x squared. How are you going to get a 1? 1 times 1. Only way you're going to be able to do it with whole numbers. Now I just got to work out how am I going to get this 1x. One of these, we're going to have a minus, right? We want to get a minus 1 there. There's either a minus there or there's a minus there, and I'm not quite sure yet. But looking at it, I think it has to be like this, right? Because if I want to make a plus 1x, I'll need 2x times positive 1 makes 2x, right? I'm thinking about doing FOIL, right? So first, outside. It's the outside that gives me 2x, and then the inside gives me minus x, and that gets me back here where I want it to be. So from there, run out of room. You should always just keep working down the page if you can. I could say that x equals minus 1, or 2x minus 1 equals 0. So if 2x minus 1 equals 0, how do I make that 0? I need x to be a half. And now it's a bit easier to go to the unit circle. So you do have to go to the unit circle again. Right. Sorry about that terrible circle. Oh, and by the way, I'd be rewriting it. Therefore, sine of x equals a half or minus 1. So I'm thinking, where does sine equal a half? There and there. Yeah. Root 3 on 2, that's your cos, but your sine's what we're looking for. Here, minus root 3 on 2. I know the pen's not very good. You know, it's just really fiddly to use. And down here, where does sine equal minus 1? That was the other solution. Okay, so then I say, therefore, x equals pi on 6, 5 pi on 6, right? So there's your pi on 6, there's your 5 pi on 6, 3 pi on 2 for your last one. 3 pi on 2. Right. Okay. Stationary points we need to find and classify. So, best way to find and classify is with a sign diagram. Now I've started drawing it like that, but there were limits. Let's actually put the limits on. It said you only need to be in the region between 0 and 2 pi. So that was our domain for our function. We've got a 5 pi on 6 here. Sorry, a pi on 6. What am I doing? Let's erase that. A pi on 6. I'll rewrite that. We've got a 5 pi on 6. And we have a 3 pi on 2. And we'll need to figure out, you know, we've got plus, minus, plus, what's going on there. Now, where's our derivative equation? Here it is. So we need to be looking at this. what I think I would do is set something up in the calculator. So imagining I'm in a test, I'll type that into the calculator and make it such that I can just keep copying it, because we're going to have to test out 4 different regions. Is that right? We'll just count them. There, 1, 2, 3, 4 different regions here. So, calculator time. I'll show you what I'm talking about. It might look a bit, yeah. So I might just have to can that. First, I need to remember the equation. So, what have I got? It'll be 2 cos 2x minus 2 sine x. Okay, 2 cos 2x minus 2 sine x. 2 cos 2 times something. I think I'll put something in actually. Now, was it plus or minus? It was minus, wasn't it? Minus sine, no, 2 sine x. Right, now the first x I'm putting in is pi on 12. Right? And that's a positive number. Now, if I go, so the pi on 12 was my x there, right? Then I had to get above pi on 6. Maybe if I went to pi on 4, so I could maybe make that a 4. That gets me into the next region, between pi on 6 and 5 pi on 6. So with a bit of cut and paste, this testing procedure can be fairly quick. Oh, I'm in degrees. Whoops. Let's fix that. Thinking, why did that come out positive? I was expecting it to be negative. Should have picked up on that a bit earlier, really. It's a bit silly. Okay, radians. That's better. We do so many different maths questions. Let's start again. Right, so the first one, pi on 12, was positive. Second one, I am actually expecting it to be negative. That's better, negative. So it's gone positive, negative. Then we had to get, could just go for pi. Yeah. We had to get between 5 pi on 6 and, what was it, 3 pi on 2. How about I just go for pi? That's between 5 pi on 6 and 3 pi on 2. So at the moment I've gone, it's a bit confusing, but I started here, positive, negative. This one will be positive. Now that's one that you can probably work out pretty easily without using the calculator. What's going to be a good one for the last one? What about if I copy this one? So I need to be between 3 pi on 2 and 2 pi. Between 3 pi on 2 and 2 pi, I mean, it can be anything. I don't know, let's go 7 pi on 4. Right. So if I type in 7 pi divide 4, that's not going to work. I'm going to have to do the times by 2 myself. And here, 7 pi on 4. 7 pi divide 4. But the point I'm trying to make is set up an equation and then just copy and paste it like I'm doing. It will make your testing a bit quicker, right? So we went positive, negative, positive, positive. Oh, that's interesting. 2 positives in a row. Let's get everything back. Right, and put those values in. Positive, negative, positive, positive. All right, so that's a maximum. this is a minimum, right? Gradient's going down, now up, and this must be a stationary point of inflection, which is interesting. So we could say, what could we say? We could say there's a maximum, a local max at pi on 6, and what's the y value? We'd have to go back to the original function, so we'd have sine of 2 times pi on 6, that's sine of pi on 3, that would be root 3 on 2, plus 2 cos pi on 6. Cos pi on 6 is root 3 on 2, so it's plus 2 root 3 on 2's. That's going to make 3 root 3 on 2. Isn't it? 3 root 3 on 2, that's too small. So there's our local maximum. Woo. Okay, so square root 3, that's about 1.8-ish. I think I'd like to know roughly how high that is in decimal numbers, because we have to do a sketch. So let's just put in 3 root 3 on 2. 3 root 3. Got to half that, so it's about 2.5-ish. 2.6, okay. 2.6. Try and remember that. So that's about, so because where we're going with this is we're going to have to draw ourselves a little curve, right? We only have to go up to 2 pi and start at 0. But I know that there's a maximum here. So this is how I do these sketches. I fill out my space. I go up to the the upper limit of the domain. So that was 2 pi. Then I go halfway. I just set up some halfway points. Not really too worried about where the grid lines are because I'm sketching. All right. So those would be on my axis there. Now that last one, that's too messy even for me. I'm going to try and write a bit smaller. 3 pi on 2. All right. Now pi on 6 would be about there. It's a third of the way between 0 and pi on 2. So it's about here. And we're up at a maximum. So let's say that's 1, that's 2. This is 2.6-ish. About here, right? And that's a point that I'm going to label on the sketch. 3 root 3 on 2. What's the y-intercept? The y-intercept is when x is 0. So that if x is 0, sine of 0 is 0. Cos of 0 is 1. So we get plus 2 times 1. So it starts at 2. I can put the y-intercept on as well. It's going to go 2 and then it's going to come back down. Let's see where the local min is. Local min happens at 5 pi on 6 here. 5 pi on 6. Okay, so I go back to my function. I put 5 pi on 6 in. Sine of 2 times 5 pi on 6 is 10 pi on 6. 10 pi on 6 is the same as 5 pi on 3. So it's minus root 3 on 2. You probably want to be referring to your unit circle there. It's a little bit hard to picture it in my brain. 5 pi on 3. But in a test, I'd be looking at a unit circle drawn on my cheat sheet. Sorry, page of notes. It's not called a cheat sheet. It's called a page of notes. What's cos of 5 pi on 6? That is minus root 3 on 2. And you've got 2 of them. That's actually similar to the last one. So instead of it being plus 3 root 3 on 2, it's now minus. Okay. Minus 3 root 3 on 2. Okay. at 5 pi on 6. 5 pi on 6, it's about here. We're going down to about there. Okay, 5 pi on 6 minus root 3. Oh, I need to fit a 3 in. Minus, oh wow, that's awful. Anyway, we'll have to do. So the curve's kind of doing that. Well, I wonder if it crosses there. Like, these things are normally pretty symmetrical. Yeah, what happens if I put pi on 2 in? Sine of pi on 2, but you got to double it. So sine of pi is 0 plus, yeah, okay, so that's actually the x-intercept there. Now, because this question's focusing on calculus, which is finding stationary points, maxes and mins, knowing that x-intercept is not essential for the sketch, I would be putting on a y-intercept, definitely putting the max, the min on. The x-intercept you can probably get away with not labeling, but I've just checked that it does go straight through pi on 2, so that is the x-intercept. And, you know, it's not going to kill you to label it, is it? So I could just say, hey, that crossed at pi on 2. All right, we've still got this stationary point of inflection. I'm going to write it out in full. No, I'm not. I'm just going to write stat. But that means stationary point of inflection. Please learn to spell it. Inflection. Right. And we've got 3 pi on 2. And we're going to have to go and find out. So the derivative. No, sorry, the function. Come on, brain, can do this. All right, we want to know where the actual point is on the actual function on the curve. So sine of 3 pi on 2 times 2, that's sine of 3 pi. So that is 0. Oh, good. Plus 2 cos of 3 pi. Well, that's also 0. Oh, okay. So this point of inflection, ooh, can he draw it? Probably not very well. And then that's got to get up to about 2 by the time it... Oh, it's a bit shaky. I think I've gone too high as well. Anyway, it's just a sketch. I'm pretty sure the period is 2 pi, which would mean it would get back to 2. If I put in 2 pi, see the problem is I've drawn this, I should be getting to here, I think. This has got to kind of come up and then inflect. It's the pen, I'm blaming the pen. Let's just check. Do you end at, so what I'm saying is this sketch ends here, 2 pi 2. I don't need to label that point, but I need to draw a sketch, so I don't want it to be too rough and ready. Let's, back on the function, sine of 2 pi times 2 will be sine of 4 pi. That's 0, okay. Plus 2 cos of 2 pi, yeah, it's 2, right? So cos of 2 pi is 1, yep, we checked. So what I would do is just put in a little arrow, but have it at about the right height. Now, say you're in a test. This question's now finished, but if this was me and I'm in a test and I'm having to do this sketch, right? I'm taking this f of x equals sine 2x plus 2 cos x, and what am I doing? I'm putting it into a calculator, right? I won't show you because the video is long enough, but I'm going here, y equals, there it is. Actually, I can show you quickly. Wow. Okay, that's not happening. All right, can't resist. Let's do it. Ooh, that's nice. What the zoom trig does, right? It's instead of the scale being 1, 2, 3, 4, right? It goes pi on 2, pi, 3 pi on 2, 2 pi. If you look at the window that's been set up, you'll see that. We don't need such, let's go -3. We don't need our, sorry, I thought I was dealing with the y. I'm trying to do this. The y's, let's go -3 to 3. The x's, all right. See, this is what I wanted to show you. See the scale, the x scaling is 1.57. What's that number? 1.57, that's half of pi, right? If pi is pi is about 3.14 approximately. So that's the calculator trying to get half pi there. Yeah, so that's a good scaling, but we only need to go from 0, we'll give it a little bit more space, to 2 pi. So 2 pi, 6.28, let's make it 7. Let's graph it again. Keep the scaling because it's really nice. There's our sketch, except we're going to start it there, right? Well, you can see that's falling right on pi on 2. Then there's our point of inflection, and we ended here, right? And I just put an arrow on it. So the calculator's given me a pretty good view there. Of course, the calculator can be finding maxes and mins. Like I'm going to go for the minimum, say left bound, right bound. The only problem is it's probably going to do it in decimals and not pi. There's my guess. Minus 2.59. See, I think on your sine diagram, if you're writing -3 root 3 on 2, it looks a bit better. But if you're graphing, you need to know about how far down the page to be going. It's a bit hard to remember what square root 3 is and work that out in your head. You might not be seeing that as a 3 pi on 2 either. Right. So the calculator, yeah, it's helpful, although putting everything in decimals, well, sometimes helpful, sometimes not. Anyway, I think I've done that question very thoroughly. Hopefully that was useful.